Hello, higher algebra students. Back here with lesson 2 of unit 6, parent graphs, domain and range. Parent graphs would be like these equations here where it's the most basic version of, for instance, a parabola with an x squared term, the most basic absolute value equation, the most basic root or radical equation without any values added or subtracted, multiplied or divided to those, just the original version, and then we'll talk about manipulating those next lesson. So again, just a reminder, looking at relationships that are functions, we're always looking for situations where we have one x that goes to two different spots as being a problem. Okay, so it's okay if we have to be loved by many, so it's okay that these all go to sixes, but it's not okay to love more than one here, so it's not okay for the 4 to go to two different values. Again, that's because if you input a 4, it's got to result in a unique value. Okay, if on this right one, if you input all these values and they result in a 6, that's just what the machine churns out. But you can't put in the same number twice like we did here and have it result in a different value on different times, because again, we don't know which one would be the result on that turn. Same thing here. This would not be a function because if you put in a 5, it can't return a 4, 5, or a 7. It has to return just one value. Again, if they all return to 5s, that's okay. But since you have a 5 that returns different values, that's not a function. This one would be a function. Again, this is the vertical line test. So we draw on that vertical line and see that we never cross in two spots. Again, that means there's never a spot where the x leads to two different y's. Okay, each one of these x's on this axis here only leads to one y value as we go along. Finally, looking down here, here you can see each one of these unique x's leads to one and only one y. In this case, same thing. Okay, nothing led to 8, but that's okay because, again, it's okay if a 4 leads to a 2 and a 1 leads to a 2 because those are different inputs and they just happen to return the same output. Similarly, down here, it's okay. These all lead to different outputs. Nothing led to a 9, but that's okay. So, so that would be a function as well. So our issues here, no function, no function. The rest of these are all functions here. Okay, so domain. Domain and range represent the possible x and y values in a graph. So for instance, when we look at all possible x values for this graph right here, we see that the lowest x value, again, the x-axis is the axis that's going horizontally here. And you can see when I put in these values that the x value gets no lower than -6. Okay, so that's the minimum x value we have here. The maximum x value, as we go to the right, ends up at 7. Okay, so that would be -6 to 7, which we would eventually write as something like this. And we'll talk about that as we proceed here in that notation. The possible y values here then would be, again, now we're looking at the vertical axis. And the vertical axis, we'd have -2, -1, 0, 1, 2, 3, 4, 5, 6, 7. So you can see the y values go from a minimum right there of -2 to a maximum right here along this line, which is 7. So we would write that as a -2, 7 with brackets, and we'll talk about brackets versus parentheses here shortly. All right. So the notation itself for domain and range, again, you're showing that range of values for x's and the range of values that the y's can be. If it's inclusive, meaning if that minimum and maximum numbers are part of the domain and range, then you would use the brackets. If they are not part of the domain and range, then you would use the parentheses. And again, this kind of goes back to the solid versus dashed line again when we were doing inequalities, where it was less than versus less than or equal to. You're going to see empty dots versus filled in dots in graphs a lot. That will show whether it's included or not included. Included would be filled in dots and not included would be empty dots, and you'll see that moving forward. If we're using infinity, okay, if we're using infinity as part of a domain or range, you would always use a parenthesis because we never technically attain infinity, since it's a concept of kind of never-ending values on the number line. So the domain and range for each of these, we'll just look through really quickly. Again, these axes we'll say are 1 unit each, so they go from 10 to -10 or -10 to 10 for each one. So the minimum x value here on this one would be along this line, which is at -7. And again, we don't see anything, there's no empty dot there, so we assume that -7 is included, and it goes all the way to 10. So the range for the x values would be from -7, an x of -7, to an x of 10. The range of y values here, again, which is the actual range, sorry, I should be careful, the domain of x values is -7 to 10. The range of y values is a minimum right there of -4. Oh, sorry, keep hitting that. -4 to a max for the y values of 8. And again, we'll bracket those because we have every reason to believe that -4 and 8 are part of our graph, and that they are included because, again, we have solid lines and we don't see any empty dots or anything like that. Okay. Now looking at this next one, you can see this graph is a little less clear in terms of where the values are. We'd have some ugly decimals if we were to do this exact. So what we're going to do is we're going to kind of approximate, and we can see that the minimum here, as far as the x values go, okay, so the domain, it doesn't quite reach -10, okay, but it's somewhere near that -10, okay? So what we're going to do is just put a parenthesis there with the -10. It's probably something like -9.65 something, just an unending decimal. Similar here, on the right side, we don't quite get to 10. We get to over 9, but we don't know where over 9. So I'm just going to, again, use 10, but put a parenthesis, meaning 10 is not included there. In the range here, the lowest this gets is something that's a little lower than -1. So I'll just use -2. Again, this is an approximation. It's probably something like -1.2345, whatever it may be. And then going up, the max would be right there or right there. They look pretty similar. And those both get to close to 4, but not 4. So we're just going to put 4 with a parenthesis there again, because that would look to be roughly the max is something that's not quite 4, but just below 4. If we have the actual equation for this graph, we could figure out what those values would actually be in those situations. Again, if there were arrows on the end of this, okay, then we would believe that it went on forever. And if it goes on forever, then then our domain would actually be infinity and -infinity on the left side. But without arrows, we don't know necessarily that it goes on forever. Okay, so now we do have some arrows. We've got some different looking graphs here. This is actually a version of the absolute value graph on the left here. I'll switch over to red to match the color of the graph. So the domain on this one, it does look like, the domain, I started to do the range there. The domain, you can see this arrow means that's going to go on forever in that direction. So the domain here, a minimum is actually -infinity, because we have no reason to believe it ever stops as it goes out to the left there. On the right side, similar, we have no reason to believe that ever stops, so the biggest x we'll get to is +infinity, okay, as that continues to go up and to the right. On the range, we can see the lowest this gets appears to be right at 0, and it does appear to be exactly 0, so I'm going to use a bracket on that side. But the biggest y we get, again, if this continues to go on, the biggest y is also going to be infinity. So this is actually a bracketed 0 on the left for the low part of the range, up to infinity on the right, which is the high part of the range. Again, we would just expect this to go on forever in both the x and y direction. All right. Looking at this next one here, which is a version of the y equals root x equation with a little transformation done to it. The domain here, I can't tell for certain, so I'm just going to put that this is -3 as my minimum x, but I don't know for sure if it's exactly -3. Again, if you look at this, it kind of looks like it stops short of the -3. So to be safe, I'm going to say that unless I have the equation to verify what the actual minimum x value is there, I'm just going to say it does not include -3. And maybe it goes down to a -2.8 or something like that. But I do see with this arrow here that this is going to continue going on forever. So it is going to go up to infinity on the right side for the x. The range here, I think it is fair to say, and again, if we had the equation, it would help, but I think it's fair to say that the range for this will minimize at a 0. So I'm going to go 0 inclusive there. Now the max for the x, again, excuse me, the max for the y, if you look at this drawing, we can't really tell what's going on. It doesn't look like it's plateauing for certain. So we don't know if it's going to just gradually increase over time or if it's actually starting to go straight horizontal or back down or anything like that. And without the equation, we don't know for certain. So for now, the safe play would again be to say that this may continue to just trend up ever so slightly. And again, if it's going forever in the x direction, then technically it would continue going in the y direction if it's continuing to go up. Again, if we know for certain that it's not continuing to go up, then the range would not max out at infinity, but rather would be some lower value here, less than infinity for that max range value. Okay, but again, we don't know for certain, so I'll put infinity there as our max for the y. We'll generally provide equations and things that will make that more definite. Okay, so now looking at just some of these parent functions, we've got the equation y equals x squared. Okay, so y equals x squared, so what we're going to do is just build this equation a little bit on our own. So let's just pick some of the more natural values for x, which would be like -2 to 2, and let's see what happens when we put those values in. So when we put in -2 for x, that would be y equals -2 squared. And again, that's very important. It's not -2 squared, okay? The -2 is in parentheses, so that does end up being a +4, okay? Because -2 times -2, which is -2 squared, negative times a negative is a positive. Just like the second one, a -1 times a -1 gives you a +1. 0 squared would be 0, 1 squared would be 1, and 2 squared would be 4. So as I graph this, it would look something like this. If I go to -2, I want to go up 4 units. Okay, if I go to -1, I want to go up 1 unit. Okay, again, that's those 2 points, -2, 4, and -1, 1. Then I have 0, 0. Then I have 1, 1, and 2, 4. So as I look at this, as you can see, if I had -3, it'd be 9. If I had 3, it'd be 9, and so on. So that continues up like this. So my graph is a parabola. And again, those arrows would just continue going because 4 would be 16, -4 would be 16, and so on. So my shape here is what's called a parabola, meaning that it has that almost smiley face feel to it where it's not straight, but it just has one clear bend in it like we see here. The domain would be here -infinity to infinity. And again, you always use parentheses for the -infinity and infinity, because again, we could continue going off in this direction and off in this direction forever. The range here, we see now very definitively the minimum this is going to hit is 0. Okay, the lowest y value here is going to be right there. The biggest y value would then be infinity, because this again will continue to go up and out as we keep going. So that is the y equals x squared parent function for this one. All right. Looking now at the absolute value of x, okay? The absolute value of x, again, if we continue to just use those same kind of values, I'll go -3 this time just to build it out one more value. Well, the absolute value of -3 is 3. The absolute value of -2 is 2. The absolute value of -1 is 1 and 0 and 1 and 2 and 3 and so on. This ends up being, as we go in either direction here, again, -3, 3 would be this top left point right there. -2, 2 is as we go down 1 and right 1. -1, 1 down to the origin, which is that original dot. And what we have here is now this V shape here with the shape. And so we're just going to, in terms of shape here, we'll just call this a V shape. Okay, the domain, as we look at this, again, this will continue on forever in either direction. So our domain remains -infinity to infinity. We have nothing that we need to avoid there. Okay, and our range here, again, we know definitively that this bottoms out at 0, so we're going to put a bracket and a 0 there, since since 0 is included in the graph. And again, this will go to infinity because this continues to go up and out, and so it will know no vertical limit on that, and so that'd be 0 to infinity. So that is again another parent function, y equals the absolute value of x. Our third parent function that was referenced originally is y equals the root of x. Now this one's unique because as we look at the x and y, if I were to put in, say, -2, -1, 0, 1, and 2 again, -2 ends up being undefined here. Okay, you cannot take the root of a negative value for this graph, and so the -2 and the -1 are both undefined values. You will later on look at some ways to kind of work around that, but right now, with what we're working with and with what this graph would produce if you were to grade it on your calculator on Desmos, you would see that we do not get into the negatives. Now, in terms of the 0 here, the square root of 0, if you were to type that into your calculator, the square root of 0, there's debate about if this is undefined or 0, but if you type it into your calculator, for instance, you would find that the square root of 0 does return a 0. So that 0.00 is going to be the first point as we work left to right with the x, where we actually return a value and not something undefined. Because if you put anything into your calculator with a negative value under a radical or in a square root, you're going to return that error undefined. Square root of 1 is 1. Square root of 2 is something undefined, so I'm actually going to make this a little easier for us and change that to a 4, because we know the square root of 4 is 2. So that will make it a little easier for our graphing purposes. So what we have here for a shape is basically half of a parabola, and we'll see that here in a moment. The domain, as you will see, so we start at 0, 0, go to 1, 1, and then we go to 4, 2. And as you could see, we'd go to 9, 3 because the square root of 9 is 3. And so the shape ends up looking something like that, okay? So it's almost like we cut off the bottom half of a sideways parabola. That would be the negative square root of x if we were to graph that. And so that ends up being really half of a parabola. Again, I'll erase that now because that's not actually part of the graph. And so the domain for this is going to be from 0 as a minimum, okay? And that's inclusive. We just showed that because 0 did return the 0 there. The max is this could go on forever. So as this continues to go to the right, that would be infinity for the domain, the max of the domain. The range, on the other hand here, okay, we see that the range does not get into the negatives, but it does get down to 0. So that's also a range starting at 0. And again, if we continue to increase the value that we're taking the square root of, then we're going to continue to increase that where that y maxes out. Obviously, the x is going faster than the y, but again, if the x never ends, then the y can never end in terms of how high we would get on this graph. If we take the square root of a billion, then the square root of 100 billion, and the square root of a trillion, and so on. So the domain and range for this are both 0 inclusive to infinity. Thank you very much for listening again. And if you have questions, as always, please ask.